My name is Zach, and this project is focused on measuring the underwater topography of a body of water. The target of this project is to develop a practical and repeatable system that can gather depth and bottom contour information in a reliable way. The customer for this design includes users such as researchers, engineers, survey teams, and environmental groups who need accurate underwater information analysis, planning, or evaluation in real time. The purpose of the product is to provide a method for collecting data about the bottom surface of a body of water in situations where direct observation is limited or it's difficult. This need exists because underwater terrain cannot easily be seen or measured without a dedicated system, which can make it harder for users to obtain useful information about depth changes, bottom features. Because of this, there is a clear need for a tool that can gather this data in a controlled and practical way. The intended audience includes anyone who needs underwater depth and contour information for surveying, research, or environmental observation. The engineering related work to meet customer needs, the design must operate reliably, remain practical in use, to collect useful measurement data, to provide repeatable results. Responsible design criteria include safety, durability, usability, and consistent performance throughout the duration of the operation. To evaluate the design, our team tested its function, consistency, ability to collect usable underwater data. Based on these results, the design is considered suitable for basic underwater surveying and topographic measurement applications.
Our design features a pressure transducer which is hooked up to a DAC which is hooked up to our laptop. The pressure transducer has liquid inside that deflects underneath the pressure of the water, which sends a signal through the DAC, which has two parallel resistors that measure the difference. This sends the data back to our computer, which we collect, and by mapping each point we are all at the pool, we put this into our code to map the bottom of the floor based off the data in our position. Now, we considered using alternatives like the ultrasonic level sensor to do something similar. Some issues with this system is it is not as accurate once the water becomes deeper, and is also has to be stable when it's mounted, which would not have been possible if we were going to be doing this in a pool or in a river. The water velocity and objects can mess up the signal as well, and when we were considering doing this in a river, it wouldn't have worked since the waters are very fast and there's rocks and other debris that we won't be able to predict. They're also really expensive, costing upwards to about $800 each. Now, some assumptions we made in order to make this project possible was that the velocity of the fluid would be negligible. Now, this is because we were doing it in a pool which has very little movement going on, considering the fact it was empty and the only people in it were the two putting it down, and they would not cause much motion. We also assumed the gravity would be constant throughout this project, and we as well assumed the volume equation in order to get density would work. So we took the water from the pool and we measured it using a flask in order to get density. We also assumed the pressure equation that we all learned in fluid mechanics would work as well.
As a result of this experiment, we were able to collect the following data, represented as a surface. The surface is a color bar indicating the maximum and minimum depths. Compared to the theoretical, there were extremes at 7 feet and 3 feet. Our model had extremes at nearly 7 feet and just under 3 feet. This is very close to the theoretical model, and the only differences we attribute are due to bias errors and our uncertainties calculated below. There were several uncertainties in this experiment. They came from our density, our linear fit uncertainty, and our maximum and minimum depths. Our density, the uncertainty, came from error propagation through an equation. Our linear fit uncertainty came from uncertainties at different depths that we propagated and quantified using the sum of squared errors. And our maximum and minimum depth were a combination of everything. We calculated the uncertainty through error propagation through an equation. These values we find acceptable. The depth was the value we were after at the end, and the uncertainties came out to about 3/8 inches to 1/2 inch in range. There were several uncertainty analysis tools that we used in this project. To begin, first we use a linear regression fit. This tool helps us to create a line of best fit among data. Our data followed a linear trend, so we used a linear regression fit. The uncertainty for this is calculated using the sum of square errors. Using that, we can then calculate our standard deviation, and then use a z-table to calculate our uncertainty. When we have data points above 30 samples, we can use the standard deviation for a population as well as the mean for a population. These equations are shown here, and the z-table is able to be used at a certain confidence interval, we chose 95, to then calculate our uncertainty. We also propagated errors through governing equations. The two equations we used in this experiment were the density equation and the pressure equation for static water. To calculate the uncertainty from these equations, we used the bottom equation. This equation uses partial derivatives under a square root and sum the squares. This leads us to our uncertainty propagated through the equation for the main variable. Several uncertainty tools were not used that were taught in this class. They include the hypothesis testing. This was not used because there was nothing to compare our mean against. Similar reason for a chi-square test. We also did not need any bins. The central limit theorem was not needed because we already had a Gaussian distribution. Chauvinet's criterion was not used because we did not feel that we needed to throw out any outliers in the data. And students' t-distribution was also not used because we always had more than 30 samples whenever we were needing to do some sort of uncertainty analysis on a population or sample.
This team reviewed 3 different options for 3 major components. The first component is the data collection device. The device selected for this experiment is the NI MindAct system that uses a high-precision 16-bit analog to digital converter. This device was selected for its high resolution and ability to meet project requirements. An alternate data collection device is the Raspberry Pi. While the Raspberry Pi is more cost-effective, it requires external programming and lacks the integrated analog to digital converter that is natively built within the NI MindAct system. An additional data collection device is an Arduino. Though the Arduino is the cheapest option and can run without a computer once programmed, it has lower bit resolution than the MindAct, which leads to higher signal noise. The second component used in this experiment is a pressure transducer, which converts pressure force into an electrical signal. An entry-level, toss-in pressure transducer was selected because it is simple, highly accurate, and highly rated for impact, thus meeting all design requirements. An industrial-grade transducer is an alternative option. While it contains a slightly higher accuracy level than the entry-level device, it contains a complex wiring system for venting that is unnecessary for the scope of this experiment. Our team also considered a research-grade pressure transducer. Though this device has extremely high accuracy, it is expensive and is not readily available for our timeline. The circuit setup used for this experiment is a voltage divider. It contains fewer failure points and stays stable as long as current is flowing. By wiring the pressure transducer in series with the resistors, we turn a simple resistance into a high-quality signal that the MindAct can easily process. A Wheatstone bridge is a viable alternative for wiring a pressure transducer. Though this option can be extremely accurate, its voltage output is measured in millivolts and requires additional amplification hardware to be read effectively. The simplest option is a direct connection. While easy to wire, this setup provides no reference to ground, meaning that it is unable to support any data collection.
In conclusion, the data collected from this experiment meets the requirements outlined. We were able to accurately obtain data about the depth and topography of the pool and to plot this data as well in a visual graph. This shows that the data about any body of water could accurately be obtained with this device. This would be especially beneficial for a few different customers. This includes marine biologists, oil companies, environmentalists, or construction companies. Anyone that's either building anything in a body of water or would like to know what the topography of the pool or body of water looks like for the wildlife that lives there. However, this could be improved in future iterations. Improvements include adding a GPS to the boat that allows us to gather the X and Y coordinates easier. Currently, we are using a measuring tape, which is slow and takes time. A GPS would shorten the time that it would take to gather this data. Another improvement is longer wiring, allowing us to measure greater depths of water and more easily measuring the middle of the body of the water. This would allow us to keep our electronics safe and away from the water while still gathering our data.